Balancing redox reactions using the half reaction method. So sometimes when you're dealing with a redox equation that you need to balance, you can easily separate it into half reactions. And if this can be done, then the balancing of the reaction can be done relatively easily. If you can't break it into half reactions, then you're going to have to use oxidation numbers and balance it that way, which is a little bit more complex. So whenever you can separate it into half reactions, then you can use this method to balance. So the other thing is that often in a redox equation that's unbalanced, it may be given to you where there are less significant reactants or products not included in the reaction that you're going to have to add in order to end up with the complete chemical reaction. So these non-redox species, things like water, or we'll see hydrogen ions or hydroxide ions, you're going to have to add them into the equation on the correct side in order to get to a balanced equation. And so to do this, we have to look at what conditions the reaction's happening under, and then we can add in those species and get a balanced equation. So when you have a redox reaction in acidic conditions, and it is able to be broken into half fractions, these are the steps that you're going to follow in order to get it to balance. So again, break it into half reactions first off. Make sure the redox species are balanced, whatever they happen to be. Make sure they are themselves balanced in terms of whatever the atom is that's gaining or losing electrons. Make sure there's an equal amount on each side. And since this is it's possible that not all of the species are recorded, if there is a number of oxygen that is uneven on one side, so one side has maybe oxygens and the other side has none, or one side has more oxygen than the other, we're going to add waters to the opposite side in order to get them to balance. But because we add waters, they come with hydrogens. This is under acidic conditions. We're going to add hydrogen ions to counteract the number of hydrogens we added in the water, assuming it did throw off the number of hydrogens. Then what we're going to do is we're going to add up the electrons and make sure the charges balance. And if one of the sides has a more positive charge, then we're going to be adding electrons to that, or essentially getting the charges to balance between the two sides. We need to make sure that between the two half reactions, the reduction and the oxidation half reaction, that the number of electrons lost equals the electrons gained. And so we will have to, in some cases, multiply the half reactions in order to get those numbers of electrons to be equal. So look for the lowest common multiple between the number of electrons in your redox half reaction, in your reduction half reaction, and your oxidation half reaction. Make sure they're equal. And then we'll be able to put the half reactions back together. The electrons should cancel out at that point. Any other common species on both sides, cancel them out or reduce them, and then you will have your balanced redox reaction. So let's try it out. This is under acidic conditions, and this one's particularly easy to break into half fractions. We have our silver doing something, and we have our manganese doing something. And so we can put our silver on one side and our manganese on the other side, realizing that is a polyatomic ion on the reactant side here. Now we can see that silver is going to be losing an electron, so we know that oxidation is loss. So we have, this is our oxidation half reaction, and then we have our reduction half reaction. So the problem with the reduction half reaction is that we have our 4 oxygens here, and there's no oxygens on the right hand side. So this is a incomplete redox reaction. Not only is it unbalanced, but it's missing some species. And so what we'll do is, because this is under acidic conditions, we're going to follow the steps that we outlined earlier. We need 4 waters on the right in order to balance the 4 oxygens on the left. But when we do that, we add 8 hydrogens on the right. So we're going to have to throw in 8 hydrogens on the left in order to get those hydrogens balanced. So at this point, I mean, we started off where the manganese is balanced. We got our oxygens to balance, and now we have balanced our hydrogens. So at this point, all of the atoms in the reaction are balanced. We need to now look at the charges. So on the right-hand side, water has no charge, but this manganese has a 2+. Over here, we have a total of 2+. On the left-hand side, this ion has a charge of -1, and we have 8 positives. So we sum those together, and that will give us a +7. So +7 and +2 obviously are not balanced. We need to balance charges, not just atoms, but charges as well. We can't create or destroy electrons, so the charges must balance. So in order to get those to balance, we're going to add in 5 negatively charged electrons. Then these will sum to give us +2 as well, as we have on the right-hand side. And so if we put 5 electrons on that side, We will then have our charges balanced as well as our atoms balanced, and this will give us our balanced half reaction done. Now, our oxidation half reaction, the atoms balanced, but we're going to have to add an electron on the right-hand side so that the sum of the right-hand side, 0, equals the sum of the left-hand side, which also happens to be 0. So if we add that one electron, that's good. But one electron being produced here is not going to give the 5 electrons needed by our reduction half reaction. So what we're going to have to do is we're going to have to get this to happen 5 times. And if we have 5 silvers, each one losing 1 electron, we'll end up with 5 electrons, and our number of electrons lost equals the number of electrons gained. And so now we have our 2 balanced half reactions, and we can add them together. Just like adding any other chemical equation, like terms are going to cancel out. Everything that's a reactant ends up on the reactant side, everything that's a product ends up on the product side, and now we have our balanced redox reaction under acidic conditions. So balancing half reactions in basic solutions, same exact process, but because it's basic conditions, we're not going to have hydrogen ions, so we are going to use hydroxide ions to neutralize those hydrogen ions. Other than that, it's going to be the exact same as under acidic conditions. First thing, make sure redox pieces are balanced. Use waters to balance any oxygens that need to be balanced. We're going to add hydrogens to balance off the hydrogen ions to balance off the hydrogens that came in the waters because of the oxygens that need to be balanced. But because it is under basic conditions, we're going to neutralize these hydrogens with hydroxide ions. But remember, under step 3, the atoms are all balanced. And so what we'll have to do is if we add hydroxide ions to one side, we have to add an equal amount of hydroxide ions to the other side as well. So balance hydroxides on both sides, whatever you add to the left-hand side, to neutralize the hydrogens, which were put there because of the hydrogens in the water, which were put there because of the number of oxygens. So we need to neutralize those hydrogens with hydroxides, but whatever number we put on one side of hydroxide, we put an equal number on the other side as well. Then we will figure out the charges by adding electrons where they need to go in order to get the charges to balance. Make sure the electrons lost equal the electrons gained. So multiply by the whatever factor you need to get to the common multiple for electrons, and then you can add the reactions together and you're done. All right, so let's try the same reaction, but let's do it under basic conditions. So we can split this into our 2 half reactions, pretty straightforward. We have our reduction and we have our oxidation. Same thing, we have in our reduction reaction, we have these 4 oxygens, so we're going to have to balance that off with 4 water molecules, but that gives us 8 hydrogens as we do that, so we have to add 8 hydrogen ions to the right, which is where we stopped in terms of atoms for our acidic conditions, but this is now basic. So what we're going to do is we're going to add in 8 hydroxides, and these guys here are going to come together, and they're going to give us 8 waters. But because we added 8 hydroxides on the left, we're going to have to do the same thing on the right. Otherwise, our atoms would not be balanced. So we're going to add 8 hydroxides on the left, which will neutralize the hydrogen ions. And we're going to add 8 hydroxides on the right. Now, if we have 8 waters on the left and we have 4 waters that we added earlier on the right, the 4 waters will cancel out with the 8 waters and leave us with just 4 waters on the left. On the oxidation half reaction, we have to add our 1 electron to get the charges to balance between the left and the right-hand side. We know that we're going to be looking at the charges in our reduction half reactions. Let's do those calculations now. So we have these guys are gone, and let's clear this up a little bit. So we have 4 waters on the right. We've gotten rid of these waters here. The hydrogens and the hydroxides are neutralized. And so now we have 8 negative charges and 2 positive charges. So this is going to leave us with a -6 on the right-hand side as our charges. And on the left-hand side, we have our -1. And we have these charges here from the hydroxide and the hydrogen are canceled out. So we just have -1 currently on the left-hand side. So in order to balance that out, we're going to have to add 5 more negatives, electrons, onto the left-hand side, just like before. So if we add in 5 electrons on the left-hand side. Our charges are now balanced between the reactants and the products in our redox reaction. So if we have 5 electrons going into their redox half reaction, we're going to have 5 electrons being produced by our oxidation reaction. So we're going to have to multiply that whole half reaction by 5, and we can carry everything down. So we have our 4 waters showing up here, our MnO4 negative, and our manganese ion as a positive. Remember, the waters got canceled out, and so actually we should have, I missed this, 8 hydroxides on the left-hand side as well. And our 5 electrons in our reduction half reaction that are going in, and our 5 electrons in our oxidation half reaction are coming out, being produced, being lost. They're going to cancel out. We can add our 2 half reactions together. Again, there's the electrons being canceled out there. Everything on the left-hand side is going to carry down. Everything on the right-hand side is going to carry down. And we should end up with our 5 silvers here, our 4 waters that got left over. They're there. Our MnO4 is going to be there. Our electrons are not there because they canceled out with the right-hand side. Again, the point was to make sure that the electrons are going to, whatever electrons are lost, are going to be gained. And our Mn manganese ion is going to get carried down along with our 5 silver ions, and our 8 hydroxides make it into the end as well. So we end up with our balanced redox reaction at the end here by writing it into 2 half reactions, balancing the species within under basic conditions, making sure the electrons are equal, and we end up with our balanced redox reaction using the half reaction method under basic conditions.